Sorry for the difficulty. Everybody should be able to hear me now. But anyway, thank you all for taking time to join us this afternoon. Today's webinar is going to be mostly applicable to customers who already own a process monitoring system for ammonium and nitrate, and those that have some familiarity with ammonium and nitrate monitoring or are seriously considering buying in the near future. The pictures in the panel here on the title slide show on the bottom left the business end of an ammonium and nitrate sensor, which we'll be discussing in greater detail. And also on the bottom right panel is a wider angle view of a monitoring system. The probe again is out of the water and mounted to the handrail with a boom and chain, which is one of our most common mountings. The controller, which is on the bottom right, is a feature of the system and is the display into the giving display of the measurements and also how to program the system. Today's topics then are around process monitoring of ammonium and nitrate, especially for municipal wastewater treatment. These subjects include sensor design and selection, a brief bit about applications, how the probes are used, probe operation and care. We'll be talking in detail about calibration, especially using the matrix adjustment procedure. And we'll also, at the end, discuss YSI IQ SensorNet versions, models of the ammonium and nitrate sensor, features and specs for you to consider. All of this today is really then centered around using ion selective electrode technology. When it comes to ion selective electrodes or YSI design, it's comforting to know that they are very similar to something we're already very familiar with, and that is the pH or ORP sensor. Both of the pH ORP and the sensors we're talking about today both operate on are electrochemical sensors that operate on a potentiometric level and include 2 or more replaceable electrodes and do not require reagents. They are then all the hardware that is incorporated into a 40 millimeter or 60 millimeter in some cases cylindrical probe, which is meant to go directly into the sample. So like pH and with all ISEs, which are very commonly used also in the lab, they measure charged substances. So only things that have a charge can be measured with this technology. NH4 plus, for example, or NO3 minus. When it comes to selection, it's important to make sure you get the right probe for your application. And there are different versions available. So you can order a probe with, for instance, just an ammonium electrode or just a nitrate electrode. There are also probes available with both ammonium and nitrate electrodes. Essential to choose the proper compensation. If you're measuring ammonium, and it is the most important measurement, potassium is the correct, the right compensation. On the other hand, if you're measuring nitrate, or nitrate is your most important measurement of the two, chloride should be your compensation. It is also important that for ammonium systems that operate on the basic side of neutral, that some pH compensation is done. And this doesn't necessarily need to be done integrated into the ammonium nitrate probe. It can be done with a separate probe also in the sample. Another thing to consider from the various brands that are available is individual electrodes, which is what is shown in the image here, versus a cartridge style, which all of the electrodes are built into and are all replaced when the cartridge is replaced. From a cost standpoint, depending on what you order and who you order from, the acquisition cost varies for just the probe and the electrodes, $4,500 up to $10,000 each. Ownership cost then also varies, and this is just kind of an annualized amount. It isn't necessarily that you'll be spending exactly this amount each year, but on average, you can expect to spend $1,000 to $2,000 per year for electrodes, and that is the main ownership cost, not including labor involved with maintenance and such. Altogether, the probe style offers a simpler and less expensive alternative to the other popular way of monitoring ammonium and nitrate in process, and that is with cabinet wet chemistry analyzers, which generally will cost 3 to 4 times as much from an acquisition perspective, and will also have generally have greater ownership costs as well. There are a number of applications when we're talking about wastewater treatment, activated sludge in particular. The ammonium and nitrate ISEs are useful for control of aeration and wasting, and also recirculation and chemical, specifically carbon dosing. Really the 4 main control handles that a wastewater operator has. So when it comes to nitrification, obviously aeration is important, and also because of the relatively slow growth rate of nitrifying bugs, wasting rate is important. With denitrification, recirculation, and carbon dosing are the key process control parameters for that, and both of those can be controlled very effectively with a nitrate probe. Ammonia-based aeration control is the relatively new type of control that has become available, and this is where the ammonia or the aeration rate is based solely on ammonia or a combination of the ammonia and DO. Many other applications are possible. The ammonia and nitrate ISEs can measure very well in a number of different applications, from the influent through to the effluent of a municipal plant and even many industrial applications. So the next several slides are going to focus on ammonium and nitrate ISE operation and care. This is a big concern for many customers that are considering and that already own ISE probes. When it comes to operation, you can ensure reliable operation by practicing the following simple procedures. And it starts really at the beginning, before you even choose or buy the probe, is selecting a representative and accessible measurement location. So it's important that where you locate the probe is representative of the process at large, and it's not maybe in a dead spot or an area that is not trending with the process. Accessibility is important because the probes will need to be, from time to time, there's going to be an operator or a technician that's going to need to handle these probes, maybe do some cleaning or for verification, and of course every now and then to change the electrodes. I have a bullet there, say observe max immersion. Generally, you want to keep the probes wet. They want to be in the water, but generally not more than 10 feet deep. They should be cleaned when necessary, and that's in the picture there. The graphic on the slide here shows proper cleaning technique for an ISE probe. Utilizing supplemental air cleaning can help keep the sensors clean. Basically, though, manual cleaning will still be necessary. The air cleaning may extend that manual cleaning interval. Also, it's necessary to verify the measurement regularly and calibrate as needed. Obviously, the sensor is no good if it's not reflecting the true changes in the process. And replacing electrodes when needed. The electrodes do become depleted, and so with all versions of ammonium and nitrate YSIs, the electrodes have a finite lifetime. We'll talk about each of these things in more detail in the following slides. Beginning with cleaning. As you would expect in a biological treatment system, slime or biomass accumulation is likely to occur in anything you put in the sample. And this can really affect the measurement reliability of the sensor. So now and then, those sensors need to be removed from the water and carefully cleaned to basically just to remove kind of the bulk contamination. We recommend you use processed water. Basically, you do not want to use VI water, especially because it can shock the measurement cell and result in a long recovery time. It may not be that it ruins the probe, for example, but you may not want to, for example, do a calibration right after cleaning it in DI water because it takes the sensor a while to adapt. However, you never do want to use soaps and detergents. These, in fact, will damage the membrane and will possibly ruin the probe, and for sure it will shorten the life. From a cleaning perspective, a soft bristle brush is recommended, like a toothbrush, for example. And I have a little video here, which I will start demonstrating proper cleaning technique. Again, the person here has got a beaker from a sample dipper, and you can see that it's got a lot of solids in it, but that doesn't really matter because all you're really trying to do is to get that slime layer, the bulk contamination, removed before you put it back into the sample. Verification is the other topic we discussed, and from time to time we recommend comparing laboratory reference measurements on grab samples with the monitoring system display. The value from the sensor minus that laboratory reference value is referred to as the error. And so if we look at the figure on the right, the error across the top going from negative 100% to positive 100%. And then the sources of the error are in the inverted triangle. So from a sampling, transportation, and storing, that, if you look at kind of the outside of the triangle, you can see that could contribute to up to 50% of error. The next step then, sample preparation, which is really important, also has a substantial impact on the potential error in the sample. Once you get that sample properly collected and prepared, and you get it to the photometer, much lower potential for error, basically within the specs of the photometer, and much, I guess, at that point, you have much less potential for error. So really, looking at that triangle, the greatest potential for error is starting at the sampling. From an acceptable error standpoint, again, this is up to the customer. These are not laboratory instruments. They are in the process where they are really subject to a lot of variable conditions, but nonetheless, customers generally evaluate suitability of these sensors based on a plus or minus 10 to 20%. Of course, if you're measuring at very low concentrations, you may want to use a tolerance of an absolute value. So, for example, plus or minus 0.2 or so. So, on the verification procedure, the sampling and sample prep are important. And so the first thing is to determine the best time to sample. You want to choose a time really when the process is stable, because if the process is changing relatively quickly, even in the time that you take the sample and note what is happening on the display, could introduce error right there. Also, it's important to only sample when you anticipate the concentration to be greater than the detection limit of the sensor, which in this case is 0.1 milligram per liter. You want to sample near the sensor, both from a horizontal perspective and a vertical perspective. So, for instance, from a vertical position, it may, if you have it on a boom and chain arrangement, it may suit you to, at least for the time of sampling, to raise the sensor a little closer to the surface. From a horizontal perspective, it is not, it's really not good practice, say, for example, to sample at the end of the process for a sensor that is actually in the process. This may seem somewhat intuitive, but there are processes, for example, complete mix processes where, in theory, the concentration is not supposed to change. But in the reality, there are micro environments out there which could be occurring such that the sensor location is at a much different condition than the effluent. And then next step would be to filter immediately into a clean sample vial. And this is important because in this mixed liquor sample especially, there are billions of bacteria, and many of these bacteria eat ammonia and eat nitrate. So they are changing the composition of the sample, even in the sample vial, such that if you wait until you get to the lab, the composition of that sample could be a lot different than when you actually took the sample. I have a brief video here showing what I mean by proper technique. So this person is rinsing out the sample dipper once to kind of using a syringe.
Muted.
A syringe filter on the end of the syringe and then pushing the sample through the syringe to get a clear sample free from bacteria that can change the sample concentration. So that is that's the proper technique and for sampling and sample prep. Now, calibration is another thing you'll need to do from time to time, and ammonium nitrate YSI
Unmuted.
pH are all all dictated by the equation here, which is the Nernst equation. Basically, the millivolt response is equal to an offset plus a slope times the log of the concentration. So that slope is 59.2 millivolts per decade. That is a property of the measurement system. And so it's important to understand this is on a logarithmic scale. So looking at the chart on the bottom, the ammonia is the blue line, ammonium response curve. And so we can see from an ammonium concentration of 1 to an ammonia concentration of 10 that a difference of 59.2 millivolts is observed. And this is also true from 10 to 100 and 0.1 to 1. So you can see that the lower the concentration, really the more sensitive to changes that probe becomes. So good sampling practice is especially important. The nitrate works the same way. It is also the same slope. It just goes in the other direction. Nitrate has a negative charge, and so it has a slope that is in the opposite direction of the ammonium. The offset, which is the U0 ion, the first term after the equal sign there, is influenced by unique sample properties. So unlike the slope, which is part of the monitoring system, the offset is really a property of the sample. So in any sample, there's going to be a variety of different substances in there of different charges, some plus, some negative, some larger, some smaller, and each of these influences the response of the sensor. And that is the picture here depicts what we call the matrix. And so the offset needs to be offset calibration needs to be done by the customer. Looking at different calibration methods, in general, we list 4 methods right here, starting with single point, which can be used to calibrate the offset. It's done in a lab with standards. 2-point, also done in a lab with standards, and the 2-point can be used also to determine the slope. These two should be very familiar to you because if you think of a pH calibration, a single point would be analogous to maybe doing a 7-point calibration. 2-point would be like doing a 7 and 10 or a 4 and 7, which enables you to get a slope. Of course, you need a standard of some kind. In terms of pH, it's your pH buffer. In ammonium and nitrate, you would need ammonium and nitrate standards. Standard addition is another technique which allows determination of both offset and slope. Generally, this is done in a bucket. You put the sample in a bucket and then you inject a high concentration standard to create a known concentration inside the bucket. And then you can determine with serial injections, you can determine both the offset and the slope. The last method is the sample calibration, or as we call it, the matrix adjustment. It's only good for the offset. It's done in the process. The sensor stays in the sample. No standards are required, but you do have to do a laboratory method to determine, reference method to determine the concentration, actual concentration of the sample. We recommend only using the matrix adjustment procedure. One of those reasons, at least for the IQ SensorNet, is the factory slope is very stable, and it will remain stable throughout the lifetime of the electrode. Also, for convenience, the sensor stays in the process, and no preparation or purchase of standards is required. Preparation, of course, is subject to errors, and also standards need to be kept fresh. So with that in mind, going to discuss how to properly do a matrix adjustment. Some of the materials you'll need include a long-handled sample dipper, 10 to 30 mil syringes with luer lock tip, and this is important. You need 0.45 micron syringe filters with luer lock fitting. The luer lock is basically a threaded fitting that secures the syringe to the filter to the end of the syringe. A push fitting can sometimes pop off. You want clean sample vials. You'll need pipettes and tips to use with your colorimeter, and test kits for ammonium nitrate, potassium, and chloride to do a complete matrix adjustment. The matrix adjustment procedure in the IQ SensorNet starts with cleaning the electrodes, as we demonstrated earlier. Also, you want to record sample conditions, specifically in this case, record the millivolt signal. Take the sample using the techniques we described. Take that sample back to the lab, measure and evaluate, and you're going to measure if you have an ammonium and nitrate combination probe, you're going to measure both ammonium nitrate, potassium, and chloride. If you only have ammonium, you only need to do potassium. If you only have nitrate, you only need to do chloride. I recommend doing duplicate or triplicate measurements on the photometer. Simply stated, if you only do one, you really don't know if it's correct. If you do two and they're very different, you're really not sure which one is more correct. 3 is preferred because then you can, basically you have a tiebreaker. Next step is to go into the monitoring system, update the sensor values, and check. So given what you know about the slope and what the concentration was between the matrix adjustments, what millivolt value did you expect? And what was the actual value? That can give you an idea of the status of the electrode and also possibly give you a clue into problems with sampling and measurement. I have another video here where I demonstrated doing the matrix adjustment in an IQ SensorNet system. So set this up in our lab. Basically, a variant probe is sitting off to the right there in a vial of sample, and is connected into the 2020 XT. And so as we zoom into the screen right here, we can see that the ammonium, nitrate, and also I've chosen to display the potassium measurement. There is no chloride electrode on this probe, so those are the three electrodes that are hooked up. So you go out to your process, and your first step to start a matrix adjustment then in the 2020 XT is to push the C button. So you push the C button for calibrate, and you get this screen right here, which shows the electrodes you have installed, variant A, N, and K, and each of those is checked off, meaning that I do want to matrix adjust each of those. The electrode zeroing is not checked. That is only for special, that is kind of a special procedure, which I'll describe when that's needed a little later. But you go in there and you push start, and right away you can see that the system is measuring the reference voltages for you for ammonium, nitrate, and potassium, and it's recording those values for you. So that's the convenience of the IQ SensorNet, is those millivolts are being stored in the system for you. So it just takes a few seconds here for those measurements to stabilize. And so this is basically setting the reference condition in the first step. And so it gives you step 1 is finished, and it tells you step 2 is to take a grab sample and determine the YSI concentration in the lab for ammonium, nitrate, potassium, and chloride. And then step 3 is to come back later and input those values into the system. So I'm going to, the video shows us pushing OK here in a moment. And basically it's going to take us back to the measurement display. And we're going to come back at another time. And there we go. Now the system is engaged, and you can continue to monitor ammonium and nitrate while you're retrieving your lab measurements. So at some time later, you come back with your measurements in hand. You push the calibrate button again, and it automatically takes you back to the screen where you left off. So now what is necessary is to enter each of those reference concentrations in for ammonium, nitrate, potassium. We don't have a chloride electrode, so we just have to enter that one manually. That will be a constant value throughout the operation. So it just shows us filling up. So the check boxes there show that I'm happy with each of these. I'm looking at the millivolt, and I'm going to keep those boxes checked. saying to proceed with the matrix adjustment at any time. If something goes awry, we don't like what we're seeing, we can break off that matrix adjustment. But this looks good, and I'm going to proceed, and it'll take me back to the it says matrix adjustment, data stored, fantastic. And so now I can go into the system, and I can switch the maintenance condition off if I've put it on. Sometimes that's done to hold the outputs. And then I can look at each of these messages that I get right here, and it tells me what the millivolt was and also the reference concentration. This is also stored elsewhere, but this is for information, and I can acknowledge each of these messages one at a time or all at once. And so now, and that's it. Basically, you're done. Now, if this had been the very first time that these electrodes were put in the sample, so these were brand new electrodes, you would also want to do electrode zeroing. And in that case, you push the C button, and in this case, you would go in there, and you would, if you were only replacing one electrode, you would only zero that one. But in this case, I'm pretending that we've changed all electrodes, and I'm going to zero those at the start. One last thing I want to demonstrate here is this calibration history report. And this is all very important information. The line item at the top shows the date and time of when the electrode was zeroed. So you can see that dV, which is drift voltage, is 0. Reference is the laboratory reference concentration that was entered. You've got the potassium concentration, the procedure, which is 1 for matrix adjustment, the temperature, and R is plus, means it was successful, question mark would mean unsuccessful. Under that, then each subsequent matrix adjustment will be listed. In this case, I only have one, but it shows the drift voltage. So this, based on when the electrode was zeroed, the drift voltage calculates how far off from the expected millivolt signal you are. So actually, minus 4 millivolts is pretty close. A perfect drift voltage would be 0, meaning that everything is ideal and perfect from the time you did the electrode zeroing to the time you did the subsequent matrix adjustment. And then it lists all the additional information there, the new reference concentration, potassium, procedure, temperature, and so on. I'll let this video run out. So that was implementing the matrix adjustment in the IQ SensorNet 2020 XT controller. And it said you push the M button to get back to the measurement display. We've covered a lot of ground here, a lot of detail as well. But I think that it's all very important for you as the customer to be part of a team that is being very successful controlling, monitoring ammonium and nitrate and controlling your wastewater process. A few closing thoughts. First, to summarize, our topic was ion selective electrodes for process monitoring of ammonium and nitrate. Again, this uses the principle of potentiometry, similar to pH or ORP. There are a lot of applications, but the primary applications are for nitrification, denitrification, and very recently, ammonia-based aeration control. The different types of probes out there include ammonium, nitrate, probes with ammonium and nitrate, and of course selecting the compensation, whether that be potassium chloride. Measurement location is very important, as well as proper cleaning and verification techniques. And we discussed specifically the preferred calibration method and how to execute that in the 2020 2020 or in the IQ SensorNet 2020 XT. So there were a few things that we would like you to consider if hopefully you already own a IQ SensorNet. But if you're considering buying IQ SensorNet, a few things we want you to know about our ammonium and nitrate ISEs. Beginning with the construction, you can see in the picture there, it's a durable stainless steel probe. You can't see it very well, but the stainless steel mesh is in front of protects the membrane. So the membrane is actually fairly delicate plastic, but the stainless steel mesh protects that so that you can do proper cleaning, for example, with the brush that we demonstrated. Our electrodes have the longest electrode lifetime in the industry. Typically, they can be expected to last 18 to 24 months. And we back that up with a 1-year warranty. So you know you're going to get, we expect you to get at least 12 months out of your electrodes. Again, the electrodes are individually replaceable. You don't have to replace a cartridge. You replace the electrodes that expire, and others that may have longer lifetime can stay in. It's a very simple replacement as well. The electrode simply threads into the port. We do require a special tool which comes with the probe, but basically it's just a little wrench shaped in the shape of the head of the electrode that enables you to put that in. It is digital technology, so the electrodes are automatically recognized by the probe and the monitoring system. So there's no need to enter any calibration coefficients or any serial numbers or any other identifying information. The system automatically recognizes those electrodes, and once they're installed, it's ready to go in the process. You would think that, well, and also I should say, we think, and this has been verified by third-party evaluations, which have been published in Water Environment Federation documents, that the ISE electrodes of the IQ SensorNet have the best performance in the business. You would think that you would pay a lot for something like this, but frankly, it's very competitive pricing, and so it won't break the bank to put these probes in your process. To offer you a little bit more incentive, we are currently running a trade-in program, 20% off the YSI IQ SensorNet 2020 XT, 10% off the IQ SensorNet 182 system, shown there. And also, these offers are good on competitor systems. So if you're looking to upgrade your IQ SensorNet, or if you have IQ SensorNet that you think it's time to replace, now is the best time to do it, at least through the end of 2016. And there's more information at the bit.ly link at the bottom. Also, we're excited about getting off the subject of ISEs just for a moment. We're excited about the Pro Sample. It's a portable sampler that is now part of the YSI product line. We'd like you to take us up on introductory offer, $2,500 for Pro Sample P, and you can either go to the link on the page there or contact your local IQ SensorNet sales representative. Of course, if you have more questions about IQ SensorNet, YSI products, World Wide Web, SlideShare, YouTube, of course telephone, and emailing YSI, or you can email me directly with specific questions. But I am going to stop talking at least for a moment or two and see if there's some questions that from the attendees that we can answer today. Thank you.
Okay, great. Thank you, Rob. We've got a lot of great questions that are coming in. The first one we'll begin with is, how often is a matrix adjustment recommended for ammonium and nitrate?
Fantastic question, and one I would expect to receive. It really depends on your application. There are times that let's talk about what causes the need for a new matrix adjustment. One of them could be a change in the wastewater characteristics. Sometimes maybe seasonal or just different operating strategy may change that matrix, and in that case a new matrix adjustment is required. Electrode does age. As I said, those electrodes do become depleted, and not real fast, but they do, and so you may find that you need to do more frequent matrix adjustments as the electrode ages. But here's what I would say for a rule of thumb. I would expect that weekly matrix adjustments would be kind of at one end of the spectrum. If you have to do them more often than not, I would consider that unusually frequent. On the other hand, I know we have customers out there who have gone 2 or 3 months between matrix adjustments, and a lot of it also has to do with the concentrations you're measuring and the exact, I guess, exactness of the measurement you're seeking. But that's a good question. Thank you.
Okay, great. On to the next question. Is a nitrate probe able to differentiate between nitrate and nitrite?
So the technology we discussed today, the ion selective electrode, theoretically nitrite can be detected with an YSI, but our version of the variant or the nitrolite will not differentiate between nitrate and nitrite. So really it's meant for nitrate monitoring, and if you need the nitrite monitoring in the IQ SensorNet, you'll have to go to an optical style probe, for example, the NitraVis NI or the NiCaVis NI.
Okay, the next question is, when you're sampling to do a matrix adjustment, if the sensor is on a PVC mount, how would you recommend sampling in the correct vertical position to get the best possible adjustment?
So let me, I guess I need to clarify what I meant by vertical position. The sensor can, if that's what you're asking, the sensor can actually be on an angle in a pipe mount. That's fine. What I was trying to get at was you want to kind of sample at the same depth as the sensor. We have many customers that use the PVC pipe mount very successfully. I happen to think that the swing mount, which is the boom and chain, is more convenient, but it's not required. So hopefully that clarifies your question.
Great. Okay, the next question is, why is it important to zero electrodes when first placing into a sample? Don't electrodes ship in storage solution to compensate for any drift?
So really the electrode zeroing is really it's like resetting the trip meter on your odometer in a car. All it's doing is setting that drift voltage to 0 for convenience for tracking the change in the drift voltage, because the drift voltage is really the main thing that as a customer you have to kind of objectively evaluate the performance of the electrode, or as I said, sometimes it gives a clue as to, maybe at one matrix adjustment you get a really far out value, far greater than what you previously was previously recorded. And in that case, you need to start looking at a very drastic change in the wastewater, or possibly improper sampling, sample prep, and measurement technique. But we always recommend zeroing the electrode when you first put them in the sample, and then keeping track of that thereafter.
Okay, the next question is, how long would you wait between cleaning the electrodes and running a matrix adjustment to make sure that the electrodes are reading correctly?
If you followed our cleaning recommendations, you really don't need to wait. You can, if you're cleaning in processed water, you can initiate that matrix adjustment procedure right away. There's no need to wait. So that's all.
Okay, the next question is, do any regulators accept YSI sensors results for compliance?
Well, if you're talking about pH, yes. If you're talking about ammonium and nitrate, no. I don't know any agencies that are going to accept let me rephrase that. I don't know any agencies that are going to accept a process measurement of ammonium and nitrate with YSI technology for compliance. There are YSIs for the lab that may be acceptable for compliance, and in that case, you need to consult your agency for what they consider acceptable. Thanks for the question. Yeah, I guess we've got time for a few more questions here. Keep them coming. If you still have questions, go ahead and enter them. I want to clarify something really quick. The first question about the vertical, the pipe mount and the vertical, I thought about that some more as we were talking. And I think the other thing you're probably asking was, with a pipe mount, obviously that it's hard to adjust the vertical position of that pipe mount when you're doing that. And I understand the question now. And so it is actually possible with the SMK mount to adjust that vertical position just for the matrix adjustment. You have to undo some hardware and such. But I think the only time that this maybe is going to be a challenge is possibly in a sequencing batch reactor, where that pipe mount by necessity has to be at a depth so that it's below the minimum water elevation. And SBRs are especially challenging for that reason and for other reasons. And since kind of got on that subject, let me just continue on with the question that wasn't asked. You've got SBR. An SBR is a fairly dynamic process. So we talked about you want to do a verification or matrix adjustment when the process is stable. There may be limited opportunities for that, for example, with ammonium and nitrate in a SBR. We have a customer who has found again, I have to credit it to them. They came up with this innovative method. And what they do is they take a bucket and they dispense, at the time they want to sample, they dispense sample into that bucket, say a 5-gallon bucket. They remove the sensor from the process and they put the sensor in the bucket. That gives them a closed, stable environment, and then they proceed with the matrix adjustment from there. Again, it's going to be, I appreciate it's going to be a little inconvenient, especially have a very long pole at the end of that sensor. But if you have 2 people, it can very easily be done, and we have as I said, we have a customer who's done that very successfully. So I apologize for not interpreting that question completely before, but hopefully those responses are very helpful.
I think we have time for a few more questions, maybe a couple more. Where is the best place to locate ammonia sensors for ammonia-based aeration control?
That's a fantastic question, and one that is challenging to answer. So I'll start by saying, where's the worst place to locate the sensors for ammonia-based aeration control? And that's going to be anywhere where the ammonia concentration is effectively zero. A couple of reasons for that. As I said, 0.1 is the detection limit of the sensor, and that's important. And it is a logarithmic relationship, so that's becomes very sensitive in that range anyway. But also, if you're always at 0, there's really no opportunity for a control. In other words, you don't know when you reached 0 exactly. So I think it really limits the opportunities for control. That being said, there are other strategies that have been used. You can, for instance, locate the ammonium sensor at the upstream end or in the primary effluent and do feed-forward control. That has been done successfully. Feedback control can still be done, though, by locating the sensor, say, mid-process. So if you've got an aeration tank, maybe you locate it at the midpoint and you adjust the aeration rate upstream. What's needed for this, though, is an understanding that if you're setting the ammonia set point at the midpoint, you need to do the investigation to figure out, well, what do I need to be by a certain point in the basin to achieve my objectives at the effluent end of the basin? And so that requires a little work ahead of time. But that being said, I think there's many different ways that ammonia-based aeration control is being implemented.
Okay, I think we have time for maybe one more question. We use the calibration method standard additions for other instruments very successfully. Why don't you recommend it for process ISEs?
I'm going to offer two very specific reasons for not wanting to do that. So for starters, you're familiar with standard additions, otherwise you wouldn't have asked the question, but you're injecting a very concentrated solution into a much larger volume. And so that solution has to be completely mixed. So first you're going to need mixing, and it's going to have to be pretty thorough mixing to make sure that the concentration within that environment is stable and uniform. But the second reason is what I mentioned about the same reason we do filter our samples. Once you've got bacteria in there, once you put that substrate in there, whether it be ammonia or nitrate, they're going to go to work immediately. And so that you're creating possibly an unstable environment by injecting a standard into the bucket, and then I don't know how long exactly it takes to do standard methods, but I think it takes, with serial injections, it's going to take enough time that the composition of the sample could be altered in the meantime. So for that reason, the sample calibration of the matrix adjustment is, for us, strongly recommended.
Great. Thanks so much for all the great questions and great responses. So thank you. I also just want to take a moment and thank you for attending today's webinar. We hope that you found all the information useful. There will be a really brief survey that'll pop up here at the end, and if you don't mind taking a moment to complete the survey, we would greatly appreciate it. And if you did have a question, that looks like there was a few more questions that might have come through here at the end, and if we didn't get to your question, we will follow up with you directly. So once again, thanks so much for attending.